Good morning. It's a great pleasure for me to be able to introduce Ron Graham. Ron Graham is at the AT&T Bell Laboratories. He got his degree in 1962 at Berkeley and has been, I believe, at the AT&T labs, although it had some slightly different name shortly ago, more or less ever since, and he's now the director of the Mathematical Sciences Division there. He's also very well known as a combinatorialist and won the prize, the Polya Prize, for his work in this area, particularly in connection with Ramsey numbers, which is one of his favorite occupations. I think that perhaps everyone knows, but I should mention if you don't know, that he is also a very well-known juggler. And in fact, I am told that he has now achieved the ultimate notoriety by appearing now in the Reader's Digest. So we'll hear from Don, who will come up and juggle the integers for us instead of his usual Indian clubs. Ron Graham.
Thanks, Andy. I might mention that at 12 o'clock, right after this talk, there will be, in fact, a small juggling group performing right out in the main lobby there. I would like to start by welcoming the high school students from the 50 or so high schools in the greater Phoenix area who have been released today, so to speak, as part of a special mathematics day, and who are attending various parts of this meeting. Now, among the most fundamental objects occurring in mathematics are the integers. So it's not surprising that some of the earliest recorded mathematical results are statements about the integers. And probably the simplest structure within the integers is that of an arithmetic progression, a subsequence of equally spaced elements. Indeed, one might easily be tempted into thinking that there can't be many interesting questions left to answer for such simple structures. What I would like to do today is to take a closer look at various aspects of this topic, including some past accomplishments, present directions, and future challenges. And in doing so, I hope to convince you that there's still a lot of life left in this fundamental subject. Now, I'd like to begin by following a tradition started by Hugh Montgomery some years ago, who opened his talk with what you might call a combinatorial theorem in search of a combinatorial proof. And I should mention that as a result of that talk, some 14 different proofs were found by various people, and these were subsequently collected and expanded into a beautiful 1987 monthly article by Stan Wagon, who was awarded a Lester R. Ford Award last summer for his exposition. So let's begin. First, definition. We'll let n denote the set of natural numbers, 1, 2, 3, and so forth, and by an arithmetic progression, we'll just mean the set of numbers of the form ax plus b, where x takes the values 0, 1, 2, and so forth. A should not be 0. And the theorem I'll mention is a theorem attributed to Mirsky and Newman. I don't think it actually ever appeared in a paper that they wrote, and it asserts the following. If n can be written as a disjoint union of arithmetic progressions, a finite number of these, n of them, say at least 2, then the largest two of these AIs must be equal. So, for example, you might write the natural numbers as the union of the evens and the odds, 2x and 2x plus 1, or 2x, 4x plus 1, 4x plus 3. Now, there's a very simple proof of this, and in some sense, slightly frustrating, that this is really, well, I'll say a little bit more about it, but basically the only proof that's known. Every talk should have a proof. Here's the proof for this talk. Suppose that we have these A1 less than or equal to A2, where now AN is strictly larger than all of the other A's, and you have arithmetic progressions whose disjoint union is N. Well, if you just take this sum of these rational functions on the left, namely z to the bi over 1 minus z to the ai, is the general term, and you expand this out, just kind of divide it out if you want, you'll see for the exponents, you'll get exactly the terms of the ith arithmetic progression. Now, by hypothesis, the union of these is exactly the set of natural numbers, and therefore, rearranging terms here, we'll assume z is less than 1 in absolute value. You get all the positive powers of z. That's easy to sum, geometric progression. It's just z to the 1 minus z over 1 minus z. Well, so what, you might say? Well, the problem with this nice identity is that if you now let z approach this primitive a sub nth root of unity, e to the 2 pi I over an. Well, you see, this root of unity is not any other a sub kth root of unity, because a sub n is the largest, it's the only one. So there's one term on the left-hand side which is blowing up, whereas the right-hand side doesn't blow up. After all, this is not 1 because n is at least 2, and so this is not the root 1. So the left-hand side blows up, the right-hand side doesn't. Contradiction, therefore, no such decomposition is possible. And the challenge here for this combinatorial theorem is to find a comparable combinatorial proof. Now, several proofs have appeared, but I think if you looked at them, you would agree that they don't have the simplicity of this. And of course, it's always possible to reinterpret this back into, some sequence of strings of zeros and ones, but that's not what's asked for here. Okay, now let's start the real talk, which begins with the following concept. We're going to be looking a lot at arithmetic progressions, but finite arithmetic progressions. And by a k-term arithmetic progression, we'll just mean a set of integers of the form b, a plus b, all the way up to k minus 1 times a plus b, a again non-zero. And our story starts with the celebrated in some circles theorem of van der Waarden of 1927, which asserts the following. For any partition of the natural numbers into some finite number of classes, say C1 up to CR, one of these CIs must contain k-term arithmetic progressions for every k. Now, you might ask, well, why not look for an infinite arithmetic progression? That would just save you a lot of trouble. But you see, right away, you're not going to find infinite arithmetic progressions because you can imagine different C's having longer and longer blocks of consecutive integers. And therefore, if you had a k-term arithmetic progression of step size A, well, this progression as it steps along must hit different C's if different C's have longer and longer blocks. So the most you could hope for is to find k-term progressions for every k. And if you haven't seen a proof of this before, and you don't have anything to do on the plane ride back home or some afternoon, you might try to prove it. There is a one-page proof, but I would be amazed if someone found it in a day. And in fact, Van der Waerden wrote a very nice account of how he did prove this, in some sense with the help of Arden and Schreier. And it gives a very nice story in kind of the history of mathematical invention. I should say a kind of a historical note here, just to clear up a little confusion. The actual paper that Van der Waerden wrote was entitled Beweis einer Bauditschen Vermutung, and people may wonder who this Baudet was. Well, it turns out he was a student who was studying in Göttingen, a Dutch student, who actually carried the problem back from Landau's seminar to Van der Waerden. And it seems that Landau actually had learned about this conjecture from Schur. Issei Schur, who was trying to prove at that time the conjecture that every sufficiently large prime p has k consecutive quadratic residues and k consecutive non-residues as well. And in fact, several days, it turns out, after Van der Waerden announced his proof, this conjecture became a theorem of Brouwer, who was a student of Schur, and in fact, who edited the collected works of Schur, and that's how we know some of this information. Now, I know at this point in the talk, people have decisions to make to find some possible alternate route to the end of the talk. You know, I see several people there with pads out, carefully taking notes, or doing a little time sharing, whatever. So I thought I would give you something to pursue this alternate route to the end of the talk, if you choose. A little exercise here. Not so hard, but it generalizes this result of Brouwer. Namely, it says to show for each k that every sufficiently large prime p, in fact, has all possible 2 to the k sequences of quadratic residues and quadratic non-residues. So you'll find k consecutive integers where they alternate, residue, non-residue, residue, non-residue, and in fact all 2 to the k occur. So that's just something to think about before lunch. Now, very soon after Van der Waerden's theorem was proved, the question naturally arose, which one of these classes? And I might say now that I may occasionally revert to the so-called chromatic terminology in this subject, namely the partitions into R classes are typically called R colorings, and the classes are called colors, and these objects, progressions in this case belonging to a single class, these homogeneous objects, are often called monochromatic. I may use that once in a while. So you might say, which one of these C's actually has the arithmetic progressions? And this was certainly asked in the early 30s by Erdős and Turon, and we need one concept to describe what turns out to be a beautiful answer to this question. Namely, suppose we have some infinite subset of the natural numbers, and we're going to define the upper density, d bar of S, just to be the lim sup, as n tends to infinity, of the number of integers up to n in your set S divided by n. So it's, in some sense, it's just kind of the fraction that are actually in S, and you take the lim sup as n goes to infinity. And beautiful conjecture by Erdős and Turon in 1936 was that, in fact, if the upper density of any set S is positive, then already S must contain k-term arithmetic progressions for all k. It's a beautiful conjecture, and a number of people worked quite hard on it with very little to show for their work until almost 20 years later, Klaus Roth showed that, in fact, if you have positive upper density for a set S, then at least it has 3-term arithmetic progressions. In fact, this result was a very ingenious use of exponential sums and was cited in the write-up for the Fields Medal, which Roth received. Not just for this result, but this was certainly one of the factors. But there was no attack beyond this. 3, it seemed to be stuck, and it took another 15 years by a completely different method before Semeredi managed to show that, in fact, this hypothesis implies that S has 4-term arithmetic progressions. And this was a very complicated combinatorial proof, so complicated that it did not extend. Something was very special about 4. And as Paul Erdős is known to do, he, in order to move the subject a little more aggressively, offered a prize for the general conjecture. And it turns out that almost instantly after he offered the $1,000 US, in those days that was real money, almost by return mail, Semeredi announced now his celebrated theorem that, in fact, if S has positive upper density, then in fact you have k-term arithmetic progressions for all k. Now, this in fact implies Van der Waarden's theorem immediately, because of course if you partition n into R classes, one of these classes must have upper density at least 1 over R, infinitely often at least 1 R through the numbers in one of the classes. Now, somewhat before this time, another development was occurring, and that's going to be a theme of this talk, to see different strands of mathematics all being brought to bear on this particular subject. And to describe this, we'll need one more idea. What we're going to look at now is a set A, just an arbitrary finite set, no structure, and we're going to look at n-tuples, x1 up to xn, formed with elements in A. So it's just the Cartesian product, if you will, A to the n. And we would like to define the idea of a line in here. Now, if we had some algebraic structure where we could add something or multiply, it's a little more usual. But here, there isn't much structure. So what is done in this case is the following. A line, combinatorial line, will consist of t points, where t is the cardinality of A, which can be written in the following way. Namely, if you look at any particular coordinate, so say we look at this coordinate, say here, C, well, that coordinate is fixed. Or if we look at a coordinate, say whatever coordinate this is, you'll see in the first point A1, the next point A2, all the way down to AT. So there are various coordinates which are either fixed at some fixed element in capital A, or they move. They run through the set A, but they all run together. They're all equal. Another way to look at this, you can think of this, I mean, the only way you can define equations here, you can say that this is a set of all x1 up to xn, so that either some coordinate, say xj, is fixed, or maybe xi equals xj equals xk. These coordinates are all equal, and they move. Anyway, there must be at least one moving coordinate, and a line is just a set of t-points, which can be written this way. So, geometrically, you can look at this as follows. So here's a simple case. Here the set A is 0, 1, 2, 3, 4. N is capital 2. Or, no, capital N is 2. Well, it's probably capital 2 as well. I don't know. And if we put these points into a 5 by 5 array, kind of indexing them this way, then what is a line? Well, a line will be any set where, now in this case, you see that the second coordinate is fixed and the first coordinate moves, so it might be any of these points, or it might be this sets of 5 points. These are lines. There's one other line in this picture, and that's almost got it. That's that line where x1 equals x2. So they're both moving together. Notice this isn't a line, because here the coordinates are not equal. They're kind of, it's a line in other geometries, but it's not going to be allowed to be a line. So things like this, or that one. And there's a beautiful result of Al Hales and Bob Jewett, which says, put it over here, that in fact, for all finite sets A and R, number of colors if you like, there's some integer capital N of A and R, so that if capital N is at least that large, and you partition the n tuples of A to the n into R classes, then one of these CIs must contain a line. Now, in a certain real sense, this can be thought of as the combinatorial core of Van der Waarden's theorem. It doesn't talk about integers at all. It just talks about finite sets, Cartesian products, and a partition. And let me show you why it instantly implies Van der Waarden's theorem and some of the more well-known generalizations. Here's why. Let's show that the Hales-Jewett theorem implies the Van der Waarden's theorem. Well, okay, suppose we partition the integers into R classes. I'm going to take for A the k-element set 0, 1 up to k minus 1. And I'm going to take capital N to be as large as it needs to be for the Hales-Jewett theorem. And I'm going to form another partition of the n tuples from A to the n. If I'm going to apply the Hales-Jewett theorem, I have to partition n tuples. And how do I define this partition? Well, I'm going to put the n tuple x1 up to xn into the C sub I prime if and only if the sum of the components, which is some integer, and therefore lies in one of these C1 up to CR, lies in the ith C. So if you want to think of saying if this has color I, then any n tuple whose coordinate sums add up to the same integer also have color I, or maybe it's color I prime. So we have a coloring of the integers, a partition of the integers in the R classes. This induces a partition of A to the n. Now there's only one thing we can do is to apply the Hales-Jewett theorem. And what's the conclusion? Well, the conclusion is one of these CI primes must contain a line. Well, okay, what is a line? Well, a line has either fixed coordinates, say A, or these moving coordinates that move 1 down through k minus 1, or 0 down to k minus 1. Now, let's go back to see how the original integers were colored, because this line lies in the CI prime. Well, you see, if you see where you got these colors from, you got it by this sum map. So if you actually sum the elements, the coordinates of the n tuples, you'll see that these sums are some number s plus, well, a certain number of zeros. Namely, if there are m columns which have moving columns, then there are m zeros, and the next one has m where 1s occur, and the last one has m where k minus 1 occurs. And these certainly form a k-term arithmetic progression. After all, m is positive. There's at least one moving column. So therefore, the ith class, the ith color, contains a k-term arithmetic progression. And since k was arbitrary, we could have done this for any k. This is Van der Waarden's theorem. So right away, Hales-Jewett implies Van der Waarden, and in fact some kind of higher generalizations, higher dimensional generalizations, which we won't look at. But kind of the picture that we have, and we have Van der Waarden, Semmeretti's theorem we saw, and I might say that this theorem was, you would have to call it a masterpiece of combinatorial reasoning, over 100 typed pages of rather, well, it's very hard. I have a certain keen familiarity with the right of Absem-Reddy's theorem, having written up the version that actually appeared in print. I took out a few months to really try to understand it, and it was just amazing. And we have Hales-Jewett that implies van der Waarden, and as a mathematician, something is shouting out that needs to be filled in this particular diagram. You know, it's 3 corners of a rectangle. Well, what should you do? You definitely would hope that there would be a 4th corner there, what you might call a density version of Hales-Jewett. You see, van der Waarden is a partition theorem. It says if you partition the integers, one of the classes has something nice in it. And Hales-Jewett is a partition theorem. You partition the intervals. Absem-Reddy is a density theorem. It says if you have a class and already by itself it has positive density, then something nice is happening. Well, you naturally look for a density version of Hales-Jewett. And so I don't know, I don't think it was so rash, but I made a conjecture some years ago that this theorem, in fact, should be true. And here's the statement of the density version of Hales-Jewett. It just says for all alphabets A and all positive epsilons, if n is sufficiently large as a function of A and epsilon, and you have a subset R of the n-tuples which has the fraction epsilon of all possible n-tuples. There are cardinality of A to the n possible n-tuples, and R has at least epsilon percent, if you will, of those. Then already R contains a line. And this conjecture resisted all efforts of everyone. And even the case of the 2-letter alphabet is not quite so simple. Let me show you. Here's the argument that shows, at least for the case if A has 2 elements. And it's an easy argument, and it shows how different combinatorial areas actually interact. Suppose you have a 2-element set A, call it, say, 0 and 1. A line now is what? Well, it's a set of 2 points where the coordinates either are fixed or they move 0, 1. Now, if you have these binary n-tuples, you can interpret these as characteristic functions of subsets of the integers 1 to n. And in the usual way of doing that is just to say that if you have x1 up to xn as your n-tuple, then I is in your set x if and only if x sub I is 1. And if x sub I is 0, then I is not in the set. Okay. Now, in those terms, what is a line? Well, a line will correspond to 2 sets, x and y, where x is a proper subset of y. Namely, x has 0s someplace where y has 1s. Otherwise, they agree. And the natural question now is, how many subsets of 1 to n can you find so that no one is a proper subset of another one? Because this is the largest number of subsets that you can have without having a line. Now, fortunately, someone already thought about that. Namely, there's a classic combinatorial theorem of Sperner from 1928 who says the answer to that question is at most this middle binomial coefficient, n choose n over 2. And you can take the ceiling function if you like. And namely, if you take all of the subsets of 1 to n which have exactly this many elements, it's clear that you can't have one which is a proper subset of another one, and this is the largest. However, since this binomial coefficient is asymptotic to 2 to the n over the square root of pi n, which is certainly less than epsilon times 2 to the n when epsilon is fixed and n is large, then any subset of a to the n of size epsilon times 2 to the n must have a pair of these comparable sets, which then translate back into 2 points that form a line. So at least this density Hales-Jewett theorem is true for the 2-symbol alphabet. And that was where it stood for a long time. Now, unfortunately, it moved. Well, maybe that's really fortunate. But in order to show you what was happening and what the next big advance was, we have to go back to some work that was being done at about the time Schur was working in algebra. And we've seen some of this material already in this particular meeting. Here, imagine that we have some compact metric space. Now, don't tune out too fast. And we have some continuous map from x to x, and typically nowadays the pair xt, we'll call it dynamical system, and we're interested in the forward orbits of points. So we take a point alpha in your set, and we'll say that that's recurrent if you can find an increasing sequence of integers, n1 less than n2 less than n3, so that when you iterate t n1 times at alpha, and then n2, and then n3, you get closer and closer to alpha as k goes to infinity. So that's just, and a theorem known as the Birkhoff recurrence theorem, although I believe it was probably known to Poincaré, says that any compact dynamical system, in fact, has recurrent points. Now, a nice extension of this, I believe first noticed by Furstenberg and Weiss, has the same setup, but instead of having one continuous map T, you have m of them, with the property that these maps commute, so that if you compose Ti and then Tj, that's the same as if you compose Tj and then Ti. So for example, if these Tj's were all powers of a particular transformation, that would be a situation this could happen. And then the multiple Birkhoff recurrence theorem says that in fact, given this hypothesis, you can always find an alpha and an increasing sequence of exponents, so that simultaneously all of these Tj's iterated n sub k times are tending to alpha. And the interesting, I mean, that's an interesting fact in itself. It might not belong in this particular talk, except that as a corollary, you get Van der Waarden's theorem rather easily, where this set now, this metric space, will denote the set of all possible colorings of all the integers. So infinite sequences of symbols 1 through r, and the distance between two of these colorings will just be 1 over n, where n is the first time where the two sequences differ, and these Tj's are various shift operators. And I won't say more about it except to say that this is the setting in which Van der Waarden's theorem follows. Now, a somewhat more substantial theorem in the same line, and we'll just have one more of these and then we're done, is the Poincaré recurrence theorem. A little more substantial here. The hypothesis is now you have some measure space with measurable sets B and some measure mu, and if you have a measure preserving transformation, then the hypothesis is like a fatter version, in some sense, of the Birkhoff recurrence theorem, that there's a set already of positive measure. In fact, if you take any set of positive measure, that's the point here, that you can find always some integer n positive, so that the intersection of A with the inverse image of T applied n times to A, already that has positive measure. And there's a very beautiful and fundamental theorem of Furstenberg from 1977, and here it is, just so that you can say that you saw it. Same setup exactly, but now you have m of these measure-preserving transformations, which commute under composition. And the hypothesis, again, it says if you have any set A of positive measure, then you can find an n, so that the intersection of A with the inverse images of each Ti to the minus n of A, that whole intersection has positive measure. And the reason that that's so striking is that as a corollary, we get Semreti's theorem out of this. It's a completely unexpected connection of earlier topological dynamics and here ergodic theory, which ties these two subjects in combinatorial theory, number theory, and ergodic theory together at a very deep level. And following this particular line of attack, Furstenberg, with various colleagues, including Katz-Nelson in particular, now have been attacking, for some 10 years, this conjecture I mentioned earlier. And I think that it's going to be the case that this will be a theorem. It says 1989. They're kind of writing up the pieces in various stages, and they really introduce a whole armada, so to speak, of new tools from ergodic theory. And one consequence of this, I'm afraid, is that, well, it's for a good cause, no doubt. And I might say, for people who are interested in following this up a little bit more, there's a book here. Oops. Oh, here we go. There, it has to work somehow. A book by Furstenberg, Recurrence in Ergodic Theory and Combinatorial Number Theory, which kind of, as of about 7 or 8 years ago, showed the approach in this kind of mandatory reading if you really want to follow this connection. Now, let me now jump back to Schur again, who actually, somewhat earlier, had been looking the following problem. He was actually looking at various modular formulations of the Fermat's so-called last theorem, x to the n plus y to the n does not equal z to the n, and you'd like to look at it mod p, and he proved the following combinatorial theorem. Namely, if you take the integers up to e times r factorial, as it came out in the proof, and you partition these into r classes, one of these classes must contain a solution to x plus y equals z. You must find 3 integers in a single class so that the sum of 2 is equal to the third. And again, if you have managed to solve the alternative route problem, which I gave earlier, here's another one which I think is a little more substantial, and it's a little more rewarding if you succeed. Namely, try to replace this number constant times r factorial with something like, say, 100 to the r, for example, or 1,000 to the r. And it's not, I think it's a very difficult problem. You know, this r factorial is about like r log r, or c to the r log r. But here, it's 100 to the r. Well, now, how is this related to what we're talking about? Well, let me mention 2 notes. A similar statement holds for solutions to x plus y equals 2z, because after all, these are just 3-term arithmetic progressions. Namely, z is the average of x and y. So there is some bound here. In fact, that's one of the last things we'll talk about, is the bound. You'll notice I cleverly haven't mentioned either Hilbert or Shelah in the talk yet, and we're almost at the end. So that's note 1. Note 2, no such statement holds for solutions to the equation x plus y equals 3z. You can actually avoid solutions to x plus y equals 3z with just 4 colors, although I'll leave it to you to actually do it. And the question is, what's going on in general here? And there's a very marvelous answer given to that question, and you need one definition. Namely, you'll call a homogeneous equation with integer coefficients, say summation I of ai xi is 0, partition regular if for every partition of the natural numbers into R classes, one of these classes contains a solution. And the theorem of Rado from 1933, who, by the way, was a student of Schur, says exactly which equations are partition regular. Namely, an equation is partition regular if and only if it can be solved in zeros and ones, and not all zero. Of course, if it's homogeneous, the all zero solution is always there and never interesting. So, for example, you see we have x plus y minus z equals 0. That's the Ture equation. Here's a solution in zeros and ones. X plus y minus 2z, that's a solution in all ones. Here's another little more complicated one. In fact, it does have a solution, although for those of you who are computationally sensitive, you'll see right away to determine whether a particular equation is partition regular is an NP-complete problem, but that doesn't slow us down here. X plus y equals 3z is pretty clear that it has no solutions in zeros and ones. So that's not partition regular. And this then led to a whole, in fact, Rado actually had the analogous theorem for systems of homogeneous equation, but it's a little more complicated definition. But you could call a set of natural numbers regular if for every partition of that set into a finite number of classes, one of these CIs contains solution to every partition regular equation. See, so now we're kind of at a iterated level, and Rado, again in 1933, at least proved that the integers were regular. So no matter how you partition these into R classes, one of the classes contains solutions to all the partition regular equations. And for 40 years, a conjecture finally settled by Deuber is the following. If you have any regular subset of the integers and you partition it into finite many classes, then one of these pieces is regular. Well, now it starts to get a little recursive, and you say, gee, what's going on here? And you might say, well, which AI? But we're not going to follow that. I want to now look at one more viewpoint here to show how we tie all these things together. Take now n integers, x1 to xn, and define by sigma x1 to xn just all the subset sums. So all the summation epsilon I xi, where epsilon is 0 or 1. And so there are 2 to the k sums here, but of course they might actually be repeated. And sigma star will denote all those sums, but throw out the choice of all zeros. So we just take the 0 away from here. So for example, sigma star of x1, x2 is just x1, x2, and x1 plus x2, those 3 sums. And you can restate Schur's theorem the following way. If you partition this initial segment of integers into R classes, one of these CI contains a set sigma star x1, x2, namely x1, x2, and x1 plus x2. And the natural, looking at it that way, there's a natural generalization which turns out was implicit in Rado's work but never explicitly pointed out, which says, in fact, not only can you find 2 numbers, x1 and x2, so the sigma star is in a class, but you can find k of these. For any k, you can find k so that all of the subset sums, except 0, lie in a single class. Now, notice this isn't true if you looked at all the sums including 0, where you were partitioning the positive integers together with 0. Because, for example, you might just partition into 2 classes. The first class has 0, and the second class has everything else. And whenever you took one of these sums, well, 0 is in one class, and everything else is in the other class, so you don't have this homogeneous property. So you might ask, well, what is true about taking all the possible sums? Well, you can't get them all in one class. And it turns out what is true was already noticed by someone that may be familiar here. Namely, in 1892, Hilbert, in a classic paper, showed that, in fact, if you partition n into a finite number of classes, one of these classes must always contain all 2 to the k sums of x1 up to xk, but translated all by some number a. So all numbers of this form, a plus. So all 2 to the k of them. And, in fact, he used this to prove kind of the simplest case of what's called the Hilbert irreducibility theorem. which just asserts that if you have a polynomial in variables, say x and y, with integer or rational coefficients, which is irreducible, then for some choice of a, an integer a, the polynomial p of x, where you substitute a in, so p of x a, a polynomial x, is also irreducible. And it sometimes makes me wonder if Hilbert had only decided to pursue the combinatorial direction that was first pointed out here, how much he might have really left his mark on mathematics. Well, no use worrying about that. No use worrying about that. Well, I might say that now all of this was beautifully subsumed by a very fundamental theorem of Neil Heinemann, who in fact showed in 1974 that if you partition the integers into finite many classes, one of these classes must in fact contain all the finite subset sums of some infinite set. So it's quite a different situation from Van der Waals' theorem. You don't get infinite arithmetic progression, but here you get an infinite set where all the finite subset sums, non-empty, are in a single class. And now this is a very fundamental tool, rather similar to the pigeonhole principle, for various attacks in infinite combinatorics and set theory. Now I want to finish by looking at the major breakthrough of last year in combinatorics, looking at the finite form. All of these theorems have finite forms. Here's the finite form of Van der Waals' theorem. It just says for every integer k, there's some least integer w of k, so that if you already partition the integers up to w of k into two classes, one of these classes must contain a k-term arithmetic progression. And a question that's been around from the very beginning of Van der Waals' theorem is, how does this grow? Well, current knowledge of the exact values are given by this table, so it's growing somewhat modestly. At 5 it's 178, 6 is way beyond computation. But the problem is that for the past 60 years, all known upper bounds on w of k grew like the Ackermann function, because there's all known proofs of Van der Waals' theorem had a double induction, and once you have that, these bounds tend to really blow up. And there was a lot of discussion as to whether or not this was in fact the truth. The true growth was really like the Ackermann function, and it wasn't quite so ridiculous, because some 10, 12 years ago, results of Paris and Harrington for some very similar combinatorial theorems were shown to have lower bounds which really did grow like the Ackermann function. And there was a tremendous surprise when, about a year ago, Seher and Shelah got a tremendous new bound on Van der Waals' function. Here is the, you can actually write it down. It's not so bad. Here is w of k, he proved, is less than or equal to this integer right here. Now, what is this integer? Well, it's a tower of 2's, which has a certain height, and the height is given by the next tower of 2's, whose height is by the next tower of 2's, and so forth. So, and there are k levels. Here, I might look at some, here are some actual values. So, from this, w of 1 is less than or equal to 4. W of 2 is 2 to the 2 to the 2 to the 2, 4. That's about 65,000. W of 3 is a tower of 2's of height 65,000. Although you know the value is actually 9, but in spite of the fact that it looks a little strange, this is a tremendous improvement over what was known. I might say the best known lower bounds are growing like k times 2 to the k due to Berlekamp, and that hasn't moved for 20 years. And I'm willing to kind of stick my neck out again here, and this has been around for a while, a conjecture that for all k, in fact, it's bounded by just a tower of 2's of height k. Now, I'd like to close with 3 problems, just to show you that there's still plenty left to do. You might look at w star of k, which denotes the size of the smallest set, so that any partition of that set S into 2 classes must always form some k-term arithmetic progression. You see, for w of k, that's just the length of the shortest interval, but maybe some crazier set actually could be smaller. Well, it turns out for 2 and 3 that's not the case, although certainly w of star is upper bounded by W. But in fact, already at W of 4, W of 4 is 35, W star of 4 is 27. Here's a set of 27 elements, so that no matter how you partition into two classes, you get a 4-term arithmetic progression. Although you can see it's solid in the middle, but near the end it kind of sprinkles out. Is this difference unbounded? Who knows? Perhaps the ratio is even tending to 0, that W star is much smaller. Have no information on that. Here is ancient conjecture, actually an old conjecture of Paul Erdős, $500. Suppose you take any assignment plus or minus 1 to the natural numbers, and now you sample it over arithmetic progressions of step size d, but which go through the origin. Does this sum in absolute value become unbounded as d and m vary? Here's what I feel is a very dangerous conjecture. I'll put it right up here. Suppose you have a subset of n cross n, so just ordered pairs of integers, with the property that the sums of the reciprocals of the square of the distance from the origin diverges. Then, is it true that this set W contains 4 vertices of a square? Or more generally, it should contain any homothetic copy of any finite set, but again, even a square. And finally, here is an ancient conjecture. Maybe Erdős is one of his most ancient. Suppose you have a set of integers which satisfies the sum of the reciprocals from that set diverges. Then is it true that this set contains k-term arithmetic progressions for all k? If this were true, it would imply, for example, that there are arbitrarily large arithmetic progressions of primes, which we certainly don't know. I think 20 is about the longest right now. And this would imply Semreti's theorem, for example. Well, unfortunately, because of time, I don't have the opportunity to go into many of the other fascinating topics in this subject, such as geometric partition theory or covering congruences or these new incompleteness results in rapidly growing functions. But much of what I've talked about today forms a chapter in a branch of combinatorics known as Ramsey theory, as Andy Gleason mentioned at the beginning, which has as its guiding principle a very nice statement that was given to it by the late Ted Motzkin: complete disorder is impossible. For those of you who would like to delve a little deeper into Ramsey theory, I can refer you to kind of a book that's okay, we've got to get it right. Okay, here we go. Well, it's okay, well, see me after the talk if you want to turn the book. Now, the last second, one might well ask at this point, who could most properly be considered the father of Ramsey theory? Should it be the brilliant Frank Ramsey, who published just one paper on the subject in 1930 and died shortly thereafter at the age of 26? Or should it be Van der Waarden, about whom we heard today, who is still living and working in Switzerland? Or perhaps it should be Ture, who originated both Van der Waarden's problem and the x plus y equals z problem as well. Or maybe, in fact, it should really be David Hilbert, who in 1892 published the first significant result in this area. Well, for my money, it's none of these. My vote would go to a person here today who's sitting and meditating in the front row, Paul Erdős. It was Paul who, together with George Sekerich in 1935, rediscovered Ramsey's theorem, and who more than anyone else has been responsible over the past 55 years for the growth and development of the subject, stimulated by his many fundamental results and his many challenging and frustrating problems. So I hope I've been able today to convince you that there's a lot left for us to do in the topic of arithmetic progressions. I invite you all to join in the fun, and thanks for coming by.